All right. Hi, guys. Hi, Sumajit. Yes, I know, I know. I know it's you. All right. So, how are you guys doing? And there is Tharian Thomas also. How you two doing? All right. So, first of all, let me welcome you guys to the Unacademy JEE English. This is a brand new channel by Unacademy, which is India's largest online platform for IIT JEE. And on this channel, everything is being taught to you completely in English. Hi, Amy. Hello, Sabresh. How are you guys? All right. Hi, Aryan. Uh, so, So this series, as you must know, that is aimed for class 11 students. So 2022 aspirants. Here we are taking all the class 11 topics from the scratch. I already have taken up these topics for 2020 aspirants. So, but there we were just quickly revising over the concepts, and here I am discussing every concept from the very scratch and explaining things to you. All right. So this is lecture one of Newton's laws of motion, and today we will start the actual physics. I'm good. I'm good, Samajit. Thank you for asking. So before we move forward, let me introduce myself one more time. My name is Rohit Dixit. I studied mechanical engineering from IIT Delhi, and I've been teaching physics for IIT JEE for almost 8 years now. All my teaching has been offline, and I've taught at some of the most prestigious institutes in India. I myself was JEE rank 447, and I've already coached many students to top ranks in IIT JEE. And moving forward, this online opportunity that I've got is through Unacademy, and let's discuss that how you can also make the most of the Unacademy subscriptions. So Unacademy subscriptions provide you live classes. You get to interact with your educators. Again, as I said, I had been in offline setup, teaching in offline setup for the entire duration of my career. This is my first online venture. So when I also looked at the Unacademy app, I realized that they have really been able to bridge the gap between online and offline classes. Their online classes are very much at par with offline classes as far as knowledge delivery system is concerned. So it's really wonderful. Plus, you have live polls and leaderboards, which make the classroom very interactive. You also have test series and analysis, again, which is a very important feature if you're preparing self-assessment and self-improvement, of course, is required. Next, you have live doubt clearing sessions, so which is again very important. I know at this hour when the J is right there in the corner, a lot of students are worried about how they will get their doubts cleared. I keep getting messages from students all the time. So don't worry, with the Unacademy subscription, that feature is taken care of. Why? Because for all Unacademy courses, it's a compulsory thing that after every 3 sessions, one session has to be a live doubt clearing session. So when you have this subscription, don't worry, you will not have any doubts left. Alright, so moving forward, Unacademy is also giving you access to India's best educators on a single platform. So not only are they giving you these awesome features, they are providing all the top educators of India to you on a single platform. So you can have access to all of them and you can study from any teacher that you feel like. Good afternoon, Krishna. How are you? So how do you get this subscription and how do you avail these benefits? So very simple. You go and install this app. Now, once you have installed the app, you go to the plus section, you select your goal as IITJ and you click on get subscription. All right. And if you will notice, the subscription fees are very economical and affordable. I mean, I have been a part of offline teaching setup, so I know the kind of fees that student pays in offline coachings. And look at this. This 24-month subscription comes at about 1,500 a month. People pay more than this for their class 6, 7 tuitions per month. I know that because I have some cousins and all who are paying much more than that for their tuitions. Even for a 12-month subscription, it comes to about 2,500 a month. So I think at these prices, this Unacademy subscription is a must-have. Now, when you're getting your subscriptions, you can also use my code RDLive. So this code will not only give you the access to all the amazing features that the Unacademy Plus provides you, it will also give you an additional 10% off in your subscription fee, which is already very affordable. It will become even more affordable. All right. So you realize this 1,500 rupee per month would reduce to 1,350 rupees per month. That's how cheap it gets. So at these prices, I think your Unacademy subscriptions are worth having, and you shouldn't be missing out on that. Now, if you're following us on the JEE English channel, you can connect with us on the Telegram app using the link shown above, so that you're not missing out on any of the scheduled lectures and sessions which are happening here on Unacademy. All right. So why don't we get started with today's lecture, which is about Newton's laws. Now, before I start with today's lecture, I'd like to remind you that in our last class, we were discussing relative motion, and there was one problem that I left at the end, and I wanted to discuss it today. So first we will go over that problem, and then we will start our discussion with the Newton's laws. All right. And by the way, I hope have you guys watched that video that I had uploaded about your biggest misconceptions about Newton's laws. So that is very relevant to this topic again. So I made this video on Monday. If you haven't watched it, you can go ahead and watch it, because there are seriously some really big misconceptions that people are following, and I wanted you guys to have a clear view of that. Anyhow, so the problem that we were discussing involved collision. It was kind of a collision problem. So this was the problem. It said three particles A, B, and C are situated on the vertices of an equilateral triangle of side R at t equals 0. The particle A starts heading towards B, B starts heading towards C, and C starts heading towards A with constant speeds. So that is how their motion will be. A will always head towards B, B will always head towards C, and C will always head towards A with constant speeds of V. So you had to find the time of their meeting. Alright, so in this problem, what essentially is happening is, okay, let me just discuss this. So let's imagine three people. Okay, so we will start with A. So there is somebody who's A, which is here. Alright, next you have B, who is situated here, and you have a third guy, C, who is situated here. So at t equals 0, all of them are situated at the vertices of this triangle, and this triangle has a side length of R. Alright, so this is an equilateral triangle. Now what happens is, imagine what will happen. A will start moving towards B, B will start moving towards C, and C starts moving towards A. So imagine what will be the position of A after some very small amount of time. So for such a small amount of time, I can imagine that A almost moves along this line AB. Okay. So after a very small time, maybe A reaches here. Alright, after a time dt, and this would be V dt. Alright, now what happens to B? Alright, so B similarly, B also moves ahead by V dt, and B reaches here. Alright, similarly C also moves ahead by V dt, and C reaches here. So this is new position of C, let's call it C dash. A reaches at A dash, and B reaches at B dash. Alright, so these are the new positions. Now what will happen? Now all of them are again trying to move along towards each other. So you will realize that this is the line of motion that they will have now. So A would try to move along A dash B dash. B would try to move along B dash C dash, and similarly C would try to move along this line, which is C dash A dash. Alright. So this is what their positions would look like. Now, because of the symmetry, because their speeds are exactly the same, this is again an equilateral triangle, by the way. Alright, I hope you guys can see that A dash, B dash, C dash will also be an equilateral triangle. Alright, just because of the symmetry. Because initially, all of them were situated on the vertices of an equilateral triangle. If you shift everyone slightly, exactly in the same angle, so the positions again will form an equilateral triangle. And now what will happen? This movement will keep on repeating itself. So A will come here, B will come here. So first we are trying to visualize how these three will end up moving, and C will come here. So after some time, what you will see is that their positions have changed even yet again. So this is what their positions would look like now. So you realize after every dt, they are on the vertices of an equilateral triangle again, and this equilateral triangle has shrunk and it is rotating. So the equilateral triangle on the vertices of which they are always present is constantly shrinking in size and also rotating. Alright. So similarly, let's just try and map a few more of these points, and then we can see a pattern of what is happening. Alright. So next again, they would be situated like this. So now if you see what is happening is, how are these guys moving? These guys will end up moving in a very interesting pattern. So B will end up taking a path like this, A will end up taking a path like this, and C will end up taking a path like this. Alright, something like that. And they will end up meeting at the centroid of the triangle. Alright, so this is how their motion would be when somebody from ground is looking at it. When someone from the ground looks at the motion of these three guys, they will see that they moved in such patterns and they ended up meeting each other at the centroid. Alright, now obviously is the tricky part. Now, how do I calculate the time? How do I calculate the time in which they are moving, in which they are meeting? So, obviously, because their trajectories are so complicated. So, if I could find the length of the path, then I could have divided with v. I would have known because the speed is constant. However, you see that the trajectory is so complicated that it won't be easy to calculate the length of the path. There is, however, another trick. The trick is you look at the motion of A with respect to B. So at any point, doesn't matter which triangle, on which triangle they are, whether they are on this triangle at any point, or on this triangle, or on this triangle, or on this triangle. So they might be on the edges of any of these triangles. What will the motion look like? See. Alright. So B will always see that if A is moving along the line joining A and B with V, and B itself was moving here with V, you realize the angle between these velocities would always be 60 because they are always at the vertices of a triangle only. So this angle would always be 60 degree. So in the reference frame of B, the velocities of A would appear as one, it will have this velocity which is V, and another it will have this velocity which will be minus times the velocity of B. So A will appear to have two velocities, one V along the line AB which is due to the velocity of A itself, and another component you will see which is because B had a velocity. So in the reference frame of B, A gets a velocity of minus V. Alright, so these are the two velocities that B will see A to have. Now you can divide these into components. Now what will you see? This is very, very interesting. Alright, now you see is, okay, let's use some other color. So in this direction it has a velocity which would be V plus V cos 60, and in this direction he has a velocity of V sin 60. Alright, so now imagine how B would see the motion of A. So B would realize that A is trying to come closer to B with a speed of 3V by 2, and it is trying to have, it also has a velocity of 3 by 2V. So what will this velocity do? Imagine, what do you think this velocity is doing? This velocity is making A go around B. So this would have made A go around B. Alright, and this velocity would have brought A closer to B. So what B notices A to be doing is something like this. Alright. Now, again, the good part is that these two directions, you will realize these two directions are perpendicular to each other, which means that they are mutually independent. And that is the trick we use to solve this problem. Alright. The trick is that you must remember that, I hope you do remember that. Okay, so let's get rid of this first. Now, as I was saying, I hope you remember that when we are talking about perpendicular directions, they are mutually independent. So when analyzing one direction, I can consider everything in the perpendicular direction to be 0 and the answer remains unchanged. So that's the trick that we use here. If I want to see in what time do they meet, then for that analysis, I can consider this to be 0 also and the answer would remain the same. And when I use that trick, it is very, very simple. A moves towards B straight in a line, and the distance covered by A along this straight line would be R, And that is why I can say now from here that time after which they meet, t would be small r over 3v over 2, which is 2r over 3v. So this is a wonderful problem. It shows you, one, how relative motion can be a powerful tool, and it also reminds you to always remember the fact that perpendicular directions are mutually independent. So when you are analyzing one direction, you can always forget everything happening in the directions perpendicular to it. So remember this trick, and then this problem is very, very easy. Now you can have any variations of this problem and the problem would be easy to solve. Now let's imagine if your problem said that A, B, C and D are on the edges, vertices of a square, and imagine they start moving like this. So these are A, B, C and D, and again they start moving such that A is always moving towards B, B is always moving towards C, and so on. Now again, right after this problem, this was one interesting problem that I wanted to discuss. So here you will realize that if they are all moving with constant speeds v, the time after which they meet would be a over v. Alright, all you need to do is find the relative velocity of one with respect to other along the line joining them, divide that with the length of the side or the distance of the line joining them. Alright, so that is how you will get the time for this. Now you can have a pentagon, hexagon, anything, doesn't matter. Alright, this is how you solve this problem. Alright, so I hope this is clear to all. Is this problem clear to all? Okay, so why don't we move ahead? Now let's start Newton's laws. Yes, RN, so which I know you have been waiting for. So before starting Newton's laws, let me tell you that this part of physics that you're dealing with is called mechanics, and we are starting with Newtonian mechanics. So what is Newtonian mechanics? So mechanics, first of all, is the branch of physics which deals with analysis and cause of motion. Okay, so here you look at motion of different objects, you are trying to analyze it, and you're trying to study the cause of it. Okay. Now, the entire study of mechanics is usually divided into three parts. Okay, so there are three branches of mechanics, three major branches of mechanics, or three ways of analyzing mechanics problems. So the first is called classical or Newtonian mechanics, second is called relativistic mechanics, and third is quantum mechanics. So classical mechanics is the mechanics which uses Newton's laws to solve all the problems. So based on Newton's laws, all right. Relativistic mechanics is obviously based on Einstein's theory of relativity. Based on Einstein's relativity. Einstein's relativity. Alright. Not really, Aryan, but it is always better if you want to note down the important points that you feel, because everything I say is not there on the slide. Okay. So one, it'll help you if you're noting things down. Second, it keeps you more involved. All right. So I would advise it would be better if you have your own pen and paper and you are taking notes. Similarly, quantum mechanics is based on quantum theory. So you have three approaches to solve mechanics problems. All right. Now, obviously, it turns out Newton's laws or classical mechanics is the easiest to solve, and that is the most relevant in our daily life problems. Alright, in daily life, when you're talking about motions of cars, you're talking about planes, everything that you're talking about, blocks, anything that you are sliding or anything that you're moving. So classical mechanics is the most appropriate approach to solve these. Now you will know that Newtonian physics obviously had some errors which were pointed out by Einstein. Alright. However, the good part is that these errors are very, very, very small under two conditions. Okay. So please note this, that all errors of this can be noted under two conditions. So all errors of Newtonian mechanics. So Newton's equations have slight errors, again, which Einstein had corrected. So obviously any result that you're getting has an error, but all errors of Newtonian mechanics are negligible if, first of all, V always is much less than C, where V is the speed of all the objects that we are analyzing. So as long as speed of all the objects that we are analyzing remains much less than the speed of light, then all the errors of relativistic mechanics, or all the things that got corrected here, can be ignored. Practically, the error is negligible. You don't even realize the error, and that is why nobody corrected Newton's equations for almost 230 years. Alright, Newton presented his equations in 1676. Einstein corrected them in early 1900s. Why people did not realize that there was an error in these equations was because practically the error is so small that you don't realize it. Okay, so all errors of Newtonian mechanics are negligible if V is much less than C. So V is speeds of objects being analyzed, or your reference frame also. Objects being analyzed, or the speed of the reference frames also. So I hope everybody remembers what reference frames are. We discussed that in kinematics. Alright. So as long as the speed of your reference frame from which you are analyzing is small, or the speed of objects that you are analyzing is much smaller than C, then all errors of relativistic mechanics, which are corrected in relativistic mechanics, can be ignored, and I can continue using Newton's laws. Similarly, also when analyzing particles of non-microscopic size. So please remember this. Now Newton's laws will also not work if you're trying to analyze particles of microscopic sizes, that is something like an electron. If you're trying to analyze the motion of an electron, Newton's laws do not seem to work. Why? Because I don't know if you've studied your Heisenberg's uncertainty principle. It says that for such small microscopic particles, or for all atomic level particles, it is impossible to learn about their momentum and position at the same time. However, when you are predicting motion with the help of Newton's laws, you are using the fact, or you are assuming that position and momentum both are known. Okay. Which part? So I was okay. I'll repeat the entire thing again. So Newton presented his laws, and he said that everything can be analyzed on the basis of Newton's laws. Alright. That turns out wrong. Einstein corrected his laws, and Einstein said, okay, you know what? Mass actually changes with speed. Mass changes with speed. And Einstein told us that m equals m naught over 1 minus v by c square. Alright, this is how the mass of an object changes with its speed. Okay. I am a dropper. क्या आप बता सकते हैं JEE Mains January time पे होगा, so that I can prepare accordingly? I think so. Most likely it should, because it is not getting delayed for this year. So that is probably because they want to have admissions at the right time the next year. Alright, so I think they would have the next JEE in Jan. Alright. Anyway, so as I said, so Einstein made a lot of corrections. He said that one, the mass is not constant, the mass changes with speed. Second, he also told if your reference frame is moving with a speed which is close to the speed of light, the time starts being slow for you. So time is not same for two observers, alright, who are moving with different speeds. time also starts becoming different, and that is why time was added as a fourth dimension. A lot of practice and clarity of your concepts. That's the only way. All right, get clarity of your concepts and then practice a lot. You will get good marks in physics. Not a problem. Okay. I don't know, but all the schools are have been conducting online classes, so I don't know. They may also delete, but as I said, as I keep saying, you should always be prepared for the worst. All right, so Saurabh, you should always be prepared for the worst. Like a lot of people were hoping that the exams will get delayed in September. It won't happen in September, but it did happen. So it's always best to be prepared for the worst. If it gets delayed, well and good. But in your mind, you only think that it is happening in Jan only. Hi Pavan. Okay. Oh, by the way, Pavan, I figured the answer to the problem that you were saying. All right. I know. I know. Okay. Okay. So I have already made such a video. It is about how to prepare for the big battle called IIT JEE. Agreed. You are right, Saurabh. But that is not your call to take. The government would take a call on that. So let's see. I don't know what kind of call they take. Maybe it will get delayed. Maybe it will happen in Jan. But you should always prepare yourself for the worst case scenario. All right. Yes, Saurabh. I agree. I agree with all this. But you and me arguing here is not going to make a difference, right? All right. Of course you can. Of course you can. Of course. But there is no surety of anything, right? So that is all I'm saying. That is all I'm saying. That nothing is sure. So always prepare yourself for the worst. All right. So in any case, shouldn't matter. Shouldn't matter. In April, you are in any case going to get a chance, even if it happens in Jan also once. So don't worry about it. Now let's focus on the topic again. So as I was saying, so Newton said that all cases of mechanics can be analyzed with his laws. All right. Oh yes, you always have my blessing, Saurabh. All the students always have my blessing. I hope that all students do very well in their exams. But it's not only my blessings that are going to be enough, it's also going to be your hard work. So you put in the hard work and trust me, it'll all be fine. Okay. Now, as I was saying, so Einstein corrected Newton's equations and he told us that mass changes with velocity, time also changes with velocity, lengths change with velocities when you're moving in reference frames. All right. So he made a lot of corrections. However, the point is all these corrections are negligible as long as the velocity, the speed of objects that you are analyzing or speed of your own reference frame is much less than c. Okay. So please remember this. As long as for the entire analysis this holds true, you will realize that even in this equation, if you notice in this equation, all right, if v is much less than c, then m is almost equal to m naught only, and you don't see a variation in mass. All right, that is why practically nobody discovered the flaws of Newton's laws for almost 230 years. All right, it took Einstein. Einstein pointed out the corrections after some 230 years. For 230 years, people kept on following Newton's laws, assuming that they had absolutely no errors and they were absolute laws. Okay, because in practical situations, most of the practical situations that we deal with, v is much less than c. So if that is the case, I can still keep using Newton's laws. All right, because the errors that are there would be so small it doesn't even matter. All right, we won't even notice those errors. Oh yes, Karan Karthik, tell me, Karan. Now, similarly, as I was saying, quantum mechanics was also developed based on quantum theory to study very small microscopic particles. It was noticed that microscopic particles behave very differently. So, if you are analyzing the motion of an electron around a nucleus, So it turns out it's not like you will find the electron moving properly like in a circle. The problem is the problem is that one time, at one instant, if you see the electron here, the next instant you may find the electron here also. The next instant you may find it here also. So where you will find the electron in the orbit is not fixed. Okay, it's not necessary that you will always find the electron moving like this. See, Newton, what he says is, if electron is here moving with a speed v, then after dt time I should find it here at a distance v dt. But that is not what happens for these. What may happen is, if the electron was here moving with v, after time dt it may be found here. Okay, then after time dt it may be found here also. You can find it anywhere in the orbit, and there is a probability function that you define. Okay, so I'm not going to get into the details of that, but point is that these electrons do not follow, or any microscopic particles do not follow, motion like Newton had expected, or we expect. Alright, that is why we had to come up with an entirely new theory, quantum theory, to explain and analyze their behavior. Alright. However, again, when analyzing particles of non-microscopic sizes, again, Newton's theories can be utilized. So that is the advantage. Now, you realize one thing. That you are in class 11th. You studied Newton's laws for the first time in class 9th. You are studying Newton's laws again, but you are still not studying relativistic mechanics or quantum mechanics, and you will not study them before your college at least. Alright. Why so? Because these theories are really complex theories. They are not easy. On the contrary, Newton's laws is very, very simple. These laws are so simple that even a class 9th kid can understand that. And that is the real advantage and real power of Newton's laws. That Newtonian mechanics uses such simple laws to describe motion, describe and analyze motion, that we can analyze them very easily. And the errors, all the errors that may come with this, are very, very negligible in all practical situations. Because in all practical situations, imagine if I'm trying to analyze the motion of this pen. This has a huge size. This does follow the fact that if its velocity is v here, in dt time it would be dt, v dt forward. Alright, so this follows all the expectations of Newton's laws. Similarly, the speeds with which this will move will not be comparable to c. So the change in mass can completely be ignored. Also, if I am another observer, which is a moving observer, analyzing this pen and analyzing this pen's motion from my reference frame, then also you will realize that slowing down of time would be negligible. Alright, so practically I don't consider all that. Practically I don't need to bother all the results of relativistic mechanics or quantum mechanics. So for practical life, alright, for the objects that we see all around us daily, I can easily apply Newton's laws and get all the answers. So that is the power of this theory. That is why we are still studying it in today's time, when the laws were first presented in 1600s. Alright. So the entire theory of Newtonian mechanics revolves around forces, by the way. So in Newtonian mechanics, everything is explained by the effect of forces. Alright. We talk about forces, we say that forces have certain effects. Alright. And we analyze everything by analyzing the forces that are acting on a body. So before we start this topic of Newton's laws, we need to understand forces first. Alright. Okay, so Pawan, by the way, are you here? If Pawan is here, please write hello. And I wanted to make a small point before I move forward. Is Pawan here? Just let me know quick. This is a small point that I wanted to make. Alright, Pawan. So, yes. So, you remember that I told you that the equation you were talking about is wrong, and you said you are getting the correct answers. Hello, Karan. So, Pawan, the point was that in most of the problems that you solve, See, F thrust actually is supposed to be U relative dm by dt, and what you were using was V dm by dt. But in most cases, most problems that you solve, you realize that U relative is equal to V. In most of the problems, U relative is equal to V only. That is why you were getting the right answer. Alright. Because you realize when a cart is moving, sand is being added, the U relative becomes equal to V. Because the initial velocity of sand in x direction is always 0. Alright. That is why you were getting the same answer. Because every problem that you solved there, U relative was V only. Okay, that is why by chance you were getting all the correct answers. When you were talking about a chain being pulled, when some part of the chain is at rest, the other part is moving with V, then the relative velocity of both the parts is again V. Similarly, if a chain is falling, if the falling part is falling with V, if the heap is at rest, again V relative, U relative is V only. So that is why you were getting all the correct answers. Okay. Yes, for in all those questions, it is a matter of chance that U relative is always equal to V. That is why you were getting the correct answers. Okay. If you use that in rocket propulsion, V and U will not be the same. U relative. Alright, there you would have gotten different answers. Alright. So I hope you are understanding why you were getting the answers with the help of that equation. Because in all your cases, U relative was always equal to V. Okay. I hope now you get. That does not make it correct. Those were only special cases of questions where U relative was always equal to V. If that was not the case, you would not have got the right answer. Alright. Similarly, as I had said, F equals ma is an instantaneous equation, and you realize you were using this. F thrust equals m instantaneous times dv by dt. This is you using F equals ma instantaneous only. That is how you use it also, right? That is how you use this. F thrust is m instantaneous times dv by dt. So F equals ma is the correct form, and it is the instantaneous form. You take an instantaneous system, you define its mass, alright, and then you take the force on this instantaneous system, you can find the instantaneous acceleration. Okay. So I hope that sorts any confusion that you may have had of how you were getting the correct answer using the equation which I am saying is wrong. Alright. Okay, is that clear? Alright, so now don't have any doubt of, sir is saying this equation is wrong while I am getting all my answers. So you were getting all your answers because by chance in all those equations, U relative was always equal to V. Alright, great. So now let's move forward and let's talk about forces. So what is a force? So force is an external activity. Speak something in Hindi. Okay, kya bolu? No, my Hindi is very, very good. Don't worry. In fact, Hindi is my mother tongue. Okay, Manjul. Hindi मेरी mother tongue है. So obviously I'm very good at Hindi. But this is the JEE English channel. I'm supposed to teach completely in English. Alright. Yes, Noman. How are you? Alright. So it's not like I'm teaching in English because I don't know Hindi or I can't teach in Hindi. ठीक है, मैं दिल्ली में ही पढ़ा रहा हूँ for the last 8 years. Okay, I have been teaching in Delhi for the last 8 years. I have been using obviously Hindi a lot in my classes. Okay. Hello, Noman Javed. So yes, I am very, very comfortable with Hindi, and for the last 8 years almost I was teaching in Hindi only. This is the first time that I am teaching completely in English. That is because for JEE English channel, Unacademy people wanted teachers who can teach in English. Okay. तो कैसा है आप लोग? Alright. So Pawan also is showing off his Hindi. Alright, in any case, let's get back to our discussion and let's get back to the language of this channel, which is English. Again, so this channel is specially designed for people who are not very comfortable with Hindi. Okay. Alright, so force is an external activity which pushes or pulls a body or tends to change the state of rest or motion of uniform motion of a body. Rohit sir knows three languages: Hindi, English, and physics language. Yes, yes, yes. Absolutely. These are the only three languages that I know. Trust me, my maths language of maths is very, very weak. Anyhow, so that is what a force is. A force is any push and pull. That is the best definition that we have. Okay, we don't have a better definition than this, by the way. All right. Again, now all the forces are there are four kinds of forces which we call fundamental forces. Now, what are fundamental forces? So, first of all, what are fundamental forces? Okay. Fundamental forces are the forces that exist in nature by default. Okay. So there is one thing that I am gonna create. So if I start pushing, this is not a fundamental force. This is something that I caused. Okay, fundamental forces are those which are not in my control. I don't control when they act, how much they act. Okay, so fundamental forces are actually the forces that your fundamental particles will also feel. All the fundamental particles feel. It is in their inherent nature. Vaibhav, we are going to be launching courses in September. I just had a word with the Unacademy team. All right. So yes, they have been planning some courses, okay, which will get launched in September. Okay. So don't worry about it, Vaibhav. All right. So as I was saying, fundamental forces are inherent property of matter. They arise from some inherent property of matter. The examples are, first of all, the first fundamental force that we discovered was the force of gravitation, which again was presented by Mr. Newton, or rather Sir Isaac Newton. So Sir Isaac Newton told us that there is a force of gravity which is acting between any two masses of the universe. Now, mass is a fundamental property. When you talk about mass, what is mass? Mass is a fundamental property of matter. Every matter has a mass, no matter what. Okay, and where does this mass come from? How and why does matter have mass? We don't know. We honestly don't know. Okay. But again, it is a fundamental property. Whenever you see matter, it will have mass. Alright. So this force is arising from that fundamental property, is attributed to that fundamental property. Just like mass is always there. Similarly, whenever two masses are there, they automatically apply the force of gravity. Now, I don't control that. Okay, I don't control, okay, whether these two should apply force on each other and how much they should apply. Like when I'm pushing my hand, I will control when to push the hand, how hard to push the hand. On the other hand, I cannot control the force of gravity acting, gravitational force acting between two masses. So that is what a fundamental force is, which is not in our control. It is a force of nature. It is a force of nature. Okay. So first one was gravitational force. Second is electromagnetic force. Again, electromagnetic force is due to charges. So electromagnetic force is the force that protons and electrons are exerting on each other, because of which all the electrons are rotating around the nucleus. All right, it is also again the force which is keeping solids, all the solid atoms tied up together, or all the forces that you see, all the bonds that are forming, are also forming due to electromagnetic forces. By the way, in your chemistry, when you're talking about bonds, everything is happening due to electromagnetic forces. All right, and then you have weak nuclear forces. Now, weak nuclear forces are interaction forces. As I said, these are nuclear forces. So inside nucleus they act inside the nucleus. So inside the nucleus, we have found two forces to be acting. One is strong nuclear, another is weak nuclear. Now, strong nuclear, first of all, let me talk to you about strong nuclear. So strong nuclear forces act between protons and protons and protons and neutrons. All right, even light. Okay, what about light? What about light? So first of all, let's talk about strong nuclear forces. All right, what are strong nuclear forces? Now in a nucleus, there are a number of protons that are packed together in a very, very close space. All right, so a number of protons are packed together, and again you may have neutrons also. So you have some protons and some neutrons which are packed together in a very, very small space. Now, obvious question is that why are they not flying apart? Because you know that charges, all protons are positively charged particles. And you know that like charges repel each other. You must have studied that. Not really. Not really. Light does not exist due to electromagnetic force. Light is a form of electromagnetic wave. So light comes from electric and magnetic fields, not force. Fields apply forces, yes, but light is a field. Light can exert force, by the way. Okay, I hope you know that light can exert a force. It's called radiation pressure. When a high intensity light is incident on something, it can exert pressure on it. Okay, so because light consists of electric and magnetic fields. So and fields can apply forces. Light can apply a force. By the way, light is not caused by force. Okay, light is electromagnetic disturbances that are traveling. By the way. Okay, in any case, so people obviously wondered, and I am sure you guys studied about current electricity in your class 10, so you should know this, that all like charges repel each other. So why is it that all the protons are getting packed into such a small space? Why are they not flying off? Why are they not repelling each other? Turns out they are repelling each other. But there is a force which is much stronger than the repulsion between like charges. Alright, which is called strong nuclear force, because this is the strongest force. This is the strongest of the fundamental forces. Yes, strong nuclear. This is strongest of these fundamental forces. Strongest fundamental force. And this is the weakest fundamental force, by the way. The force of gravity is the weakest fundamental force. Alright. So as I said, these are the four important categories of fundamental forces: electromagnetic, gravitational, weak nuclear, and strong nuclear. So strong nuclear force is the force which acts between proton, 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 neutron, and neutron, neutron. So it acts between all the nucleons. These are all called nucleons, or acts between nucleons. Nucleons are the proton and neutron together are called nucleons, so because they constitute a nucleus. So strong nuclear forces act between nucleons. And similarly, weak nuclear forces act between protons and some other subatomic particles, which again you do not talk about. So that is why I'm not going to get into that. Okay, weak nuclear forces act between particles. Okay, a lot of particles are there. So subatomic particles. So these are particles that act between other subatomic particles and protons and neutrons. All right. So act between other subatomic particles. So one example is neutrino. There is a subatomic particle called neutrino. Neutrino shows weak nuclear interactions. Okay, a neutrino is a very small particle which has almost zero mass and no charge. So that is why neutrino was something which was not which was difficult to discover. You know, in class 11th we discussed a lot about gravitation early, nearly 80%. Okay, what about quarks? Okay, so that is completely different. Amy, we are not going to get into that. But weak nuclear interactions are not among quark. What is holding quarks together? Again, that is a very different thing. We believe that there is something called gluons. Okay, so the quarks are glued together by particles called gluons. Again, I'm not going to get into that. Okay. So essentially the idea is both these forces exist inside the nucleus only. So both these forces exist inside the nucleus only. So please remember that. Okay. Okay, where do I write that? Mm-mm-mm. Maybe I can write it here. Both exist inside nucleus. And both are very, very short range forces, by the way. Okay. All right. So please remember, practically, that is why practically all the forces that we encountered are either electromagnetic in nature or gravitational in nature. Why practically you are not going inside the nucleus. So practically you don't bother about the lower two forces. You don't bother about the weak nuclear and strong nuclear forces. You don't even study them. Practically all the forces that you see are in one form or the other manifestation of either electromagnetic force or gravitational force. All right. Now also on a macro level, we can classify these forces. Okay, so we can classify these forces. Not really, not really. We can classify these forces into two categories, which are called contact forces and non-contact forces. So let's talk about that now. So before we start that, let's talk about some characteristics of forces. What are forces? What can they do? So a force tries to produce. It can either produce or it will try to produce motion in a body at rest. It can either stop or try to stop a moving body. It can also change the direction of a moving body, and it can also change the shape of a body. So these are the four effects that forces can have on bodies. Okay. Next, as we said that on a macro level, we can divide all forces into two categories, which are contact forces and non-contact forces. Now, non-contact forces are also called field forces. So these are non-contact forces. Alright, so what are non-contact forces? So all non-contact forces are result of some corresponding field. Like gravitational force is exerted by gravitational field. Now what gravitational field is, we will study later. But all I am telling you is that all these forces, non-contact forces, are acting from a distance. The force of gravity acts from a distance. Okay, two people don't have to touch each other to exert the force of gravity. Similarly, two people don't have to touch each other to exert the electromagnetic forces. So how are these forces happening, or how are these forces being applied? So we introduce the okay. All right, why not? All right. Okay. Okay, please write it down. No problem. I will even make it like this. Okay, or maybe enlarge it so that you can note this. So weak nuclear, as I said, weak nuclear force. One example that I can remember from the top of my head is of neutrinos. As I was telling you later, towards the end of your class 12th, you will study about this particle called neutrino. So neutrino was supposed to be a very small particle which has almost zero mass and absolutely no charge. So how do you detect such a particle? So whenever you're talking about, how did we detect electrons? All right, when electrons are, okay, all right, okay. So when electrons are passing through any area, what I can do is I can either keep something, so they will strike it, they will exert a force, so I know, okay, there is something, because I can't see electrons with naked eyes. So how do I detect electrons? So either I can keep a plate, maybe if electrons are falling, they will exert some force, or maybe I can put them in electric fields. Alright, if I put them in electric fields, they would start deviating, and then I can make them land on some photographic plates. They will produce some patterns. So that is how I can detect these small particles. But the problem with neutrino was that neutrino is so small, and has such a small mass that when I keep something in the path of neutrino, a neutrino just goes through it. You realize that every atom has a lot of empty space with the nucleus and the electrons. So neutrinos being so small will pass through these empty spaces, not even interact with the atom. So you cannot detect them. Similarly, since they have no charge, they do not respond to electric fields. So how do you detect these? turns out they respond to weak nuclear interactions. They feel the force. Can a fire have a shadow? Okay, so first of all, you need to understand what shadow is. Okay, let's not get into that. What we'll talk about optics later. Right now, let's just stick to this. Okay, okay, let's just stick to this. Smaller than quarks, yes, yes, yes. Neutrino is something completely different. Almost zero mass. You realize all protons and all neutrons are made up of 3 quarks each, and all quarks have identical masses. Okay, so there are around 6 type of quarks, by the way. I'm not going into those details, but quark is supposed to have a huge amount of mass. Huge amount of mass. A neutrino has almost a zero mass. Okay, has almost a zero mass. It was okay. So let me tell you briefly. Maybe we will again discuss about this in class 12th when you're talking about nuclear physics. Then I will tell you about neutrinos. Okay, but neutrino was obviously not detected, but Planck, Planck's constant, that Planck predicted that there must be a particle. Why? Because in nuclear reactions, energy conservation and momentum conservation was not holding up. All right, so some people thought that maybe energy conservation and momentum conservation do not hold true for nuclear reactions. But again, as I have said in some lectures that I have taken, that that is one belief that scientists have, that nature does not behave one way sometimes and another way sometimes. It should have consistent behavior. So if everywhere it is showing energy conservation and momentum conservation, it should show that in nuclear reactions also. So Planck proposed, all right, Planck proposed that there is one particle that we are missing. There must be a particle which is carrying the rest of the momentum and rest of the energy that we are finding missing. All right, and if we consider that particle, then all our equations will balance themselves out, and we will find that energy conservation and momentum conservation must be holding true. So Planck proposed the existence of such a neutrino in early 1900s. All right, and later the neutrinos were discovered, I think, in around 1930s. All right, so it was tough to discover neutrinos, but yes, neutrinos got caught because they show weak nuclear interactions. So that is the only way you can detect a neutrino, by the way. Now a lot of countries are also setting up neutrino labs. By the way, India has set up a neutrino lab where neutrinos are going to be studied. They did that very recently, only a few years back only. Okay, all right. So let's get back to non-contact forces. All right. So as I said, so second point of this slide. Okay, so I am going to talk about this. So as I said, whenever we see forces acting from distance, and I wonder that how is it that these two are able to apply force when they are not even touching each other? Because in our experience, whenever you want to apply a force, you have to touch something. All right, so how can you apply force without touching something? Then we came up with the concept of fields. We said that there is a field which is an invisible thing that everything creates. Okay, so gravitational field is what causes gravitational force. So we now believe that whenever you have a mass, it is creating a gravitational field all around it. It is an invisible thing, but once this field is created, any mass that comes into this field will start feeling a force. It is the field that is telling this mass where to go, how much force to feel. So who's applying force on this? It is the field that is reaching this guy. All right, so that is the idea that we have. We will talk about fields in detail when we talk about gravitation. So right now, I just wanted to introduce the idea of fields. So all non-contact forces are attributed to some fields. So we say any non-contact forces is acting because of some field. So electric forces are acting because of electric fields. Magnetic forces are acting because of magnetic fields. And gravitational forces are acting because of gravitational fields. So that is what we say here, that gravitational force is a result of gravitational field. If a mass is here and if some gravitational field is reaching here, then it will feel the force of gravity, otherwise it will not. If it does not have a gravitational field reaching it, it will not feel the force of gravity. Similarly, electrostatic forces are applied by electric fields and magnetic forces are applied by magnetic fields. Okay, I hope that is clear. Or were you talking about the last slide, Amy? So if that is clear, should I move ahead and move on to the next slide? All right, should we move ahead to the next slide then? Please let me know if you guys are ready for the next slide. All right, since no response, I'm going to move forward in any case. Now, what are contact forces? Obviously, when one body applies force on another by means of direct contact. All right, hello Krunal. Okay. Then such forces are known as contact forces. Some examples are normal reaction. We will be discussing these, what these are. Tension, spring force and friction. Alright, these are some examples of the contact forces. Now, the very important point that you need to note. Although all forces are in nature are result of some field. So all forces are eventually. I was having fever, so I was not able to. Fever. Okay, no problem, Kronal. So please remember that there are only four fundamental forces of nature, and every force that you see has to be in one form of these four forces only. And as I said, since two forces act inside the nucleus, so any force that you see, be it normal reaction, be it tension, be it spring force, or any force that you see in the world, any contact forces that you are seeing are also in one way or the other either gravitational force or electromagnetic force. So let me tell you this again. All forces that you know of are eventually either gravitational force or electromagnetic force. Okay. Now, as I was saying, that all forces in nature are result of some field. We know that all four fundamental forces are field forces. They act from distances. Okay. On macro level, we see objects touching each other, which does not take place in micro level. So when the distance between two objects is too less to be seen by the naked eye, we see the objects to be in direct contact and the force between them as contact force. So what do I mean by that? Hi Guransh, I'm good. What do I mean by that? Let me see. When I'm saying that this is my hand and when I put my finger here and touched it, it felt a force. Now truly, these two will never touch each other. Never. Alright. How is the force acting? See, this hand has some atoms or molecules. Alright, so these atoms and molecules have their own nuclei and electrons. Alright, so imagine this. And my finger has its own atoms and nuclei and electrons. Alright. Okay, I'm back again after a few days as I was not well. Alright guys, you should take care of your health. You cannot afford to be falling ill. So what is happening is when I'm bringing this hand and this finger together, so I'm bringing these two guys together. Alright, I'm bringing the electrons of both together or close to each other. You realize, I hope we will talk about this in class 12th, but two charges exert a force on each other, which is given by the equation k q1 q2 over r square. So what happens if r is becoming smaller and smaller? So it's not like they are not exerting any force when they are this distant apart. Alright, yeah, I am going to explain that once. So the force that I'm feeling when I'm touching my hand with my finger is this force that these electrons are applying on these electrons. That is what I have said. When you're touching your hand, the force that you're feeling is the force with which the electrons of my hand are repelling the electrons of my finger. Okay, I hope you understand that. Is that understood? That is the force that I'm feeling. I'm feeling pushed, right? My hand starts feeling pushed. My finger starts feeling pushed. Why is that? Both the electrons are repelling each other. They are pushing each other apart. That is what I'm feeling. Okay, so first, I hope you understood that. Second, what I'm saying is that you will say that electrons can repel each other from a distance also. Absolutely. But from a distance, you realize all these atoms are neutral. All these atoms are neutral, so neutral objects are not essentially feeling much forces. What happens on the other hand is that when I am bringing them closer, your hand is a solid. So do solids not have atoms? Pawan, do solids not have atoms? Are solids not made up of atoms and molecules? What are you saying? All solids are also made up of atoms and molecules only, isn't it? Of course, your hand is a solid. No, all matter is made up of atoms. All atoms are collection of floating subatomic particles, right? Isn't that? I hope you got what I'm saying. Again, let's get back to the discussion here. Now, what happens when I bring them really close? When I bring them really close, now the electrons are so close that the force that they are applying on each other becomes much greater than the force that this nucleus must be applying on this. All right. I hope you realize. So when they are far at a distance, this is neutral. This has nucleus and electrons. This is neutral. This is nucleus on electrons. They are not applying any force. But when I keep on getting them closer and closer, now what happens is the outermost electrons are getting so close that they start applying a very high force. You see this equation. This is the equation which tells you what is the force between two charges. I don't know if you studied this in class 10th, but you will be studying this in detail in class 12th. What I am trying to tell you right now is what happens when you try to bring r towards 0. If you start making your r very small, the separation between two charges very small, then the force increases. That is what is happening when you are bringing your hand and your finger very close. If you bring them very close, then the r becomes so small that the force of repulsion between these electrons becomes significant. However, these two electrons will never touch each other, by the way. These two electron clouds will never touch each other. So this has electrons revolving around the nucleus. This has electrons revolving around the nucleus. They can never touch. Why? If they touch, then R is 0. If they touch, then R is 0. Alright, so please note. So two bodies never truly touch. As that would make the electric forces infinite. Alright, so they are not truly touching. However, what happens is that the R becomes very small. Very small, in fact. So distance becomes so small so that the force is significant. That is why you're feeling a big force, because electrons have charges which are of 10 to the power of minus 19 coulombs. Alright, so the charge is so small, but you are still feeling a huge force because you made the R so small. So very small. Practically we say they are touching. Alright, because we can't see it not touching without the a microscope. Naked eye feels that they are touching. Alright. Practically we say they touch. So that is the point I was making, Aryan. Alright. Yes, R is actually tending to 0. Absolutely. Practically we say that they touch. So that is what is happening. Alright, that is the point that I wanted to make. That when you're talking about contact forces, no bodies ever come in contact truly. This is only a practical thing. Practically, we are talking about a contact being made. A contact being made is essentially if the distance is so small that my naked eye cannot see that distance. there is still distance between my finger and my hand. Just that I can't see that distance from my naked eye. It's very, very, very small. But there will always be some distance, okay? Even if it is tending to zero. Alright, so that is the logic. That essentially it is still electromagnetic force which is still acting from a distance, just that distance is negligible, and this kind of force I call contact force, which practically seem to have to start acting only after contact is made. Alright, I told you this force will start becoming significant only if R is very, very, very small. Why? Because the charge of an electron is so less. Alright, the charge of an electron is so less that this force, I will only start feeling this force if my R becomes very, very small. So I don't feel the force even here. Even here, because all the atoms are neutral. So atom as such are not applying a net force. It's only if I bring them that close, that these electrons are so close to each other that they can start pushing each other. Their force becomes so strong that it is more than the attraction force between the nucleus and the other electron. Alright, that is the point. See, when these two bodies are coming together, what is happening? What is happening? That these electrons are repelling these electrons. However, this nucleus is also attracting these. I hope you will see that this nucleus will also attract these. But when I am bringing them this close, then what is happening is that because the distance between electrons is so small, that the repulsion force starts becoming much greater than the attractive force, and that is when I start feeling a force. Alright, so these forces, but we aren't touching, then how are we holding objects? It is because of force. You don't need to touch to hold objects. Alright, what happens? Okay, what happens if I have a piece of paper and if I'm blowing air on it? Alright, if I'm blowing air on it, I can hold it in air, right? Amy, I hope you're getting it. It's the force that holds things, not contact. Contacts don't hold things. Alright, it's the force that holds things. Have you never held anything on top of a magnet? Have you never kept two magnets together? One will stay in air. Imagine that. Imagine that. Imagine that. Take two magnets, put both their poles on one side. One magnet would hang in air. That is how you are holding things. It is the force that is keeping things held. Alright, the force is real. The contact may or may not be true, but the force is true. Okay. Alright. So if you allow, then should we move forward? Okay. So now let's start our discussion of the common forces that we are going to encounter. So in mechanics, as I said, we are only be dealing with this year in your class 11. We will only be dealing with the contact forces that you see all around and the force of gravity, which is weight. Okay. So the first very common force that you will come across is weight. What is weight? So this is the force of gravity which the earth exerts on any object. That is the weight of an object. Alright. Now near the surface of the earth, this force is taken as mg, where g is obviously, you guys should know, acceleration due to gravity, which has a value of 9.8 meter per second square. Now weight of a body always acts towards the center of the earth because that is the direction in which the gravitational force acts. And in most practical cases, we take it to be vertically downwards. Alright. So why in most practical cases, you see your ground as flat, you don't see the curvature, you are so close to the ground. So you will just treat your force, your weight to be vertically downwards only. Alright. I hope you're clear about that. It is only if you know, in some special cases that you will need to bother about it being towards the center of the earth. Alright. So this is a very fairly simple. So wherever you see a block, alright, the first thing that you know is that there is one force acting on it, which is the force of gravity. So if you ever see a block of mass m, we will talk about this, you immediately apply a force on it. The force has to be vertically downwards and it has to be mg. Alright. You should know that all forces are vector quantities, so we will need to specify their magnitudes as well as directions. Okay. Next, let's talk about normal reaction. What is normal reaction? So this is interesting, by the way. So when two bodies are kept in direct contact, they both apply forces, contact force on each other to prevent a body from occupying the same space. All right. So what do I mean by this? What do I mean by this? Let me tell you. Okay. So something. Imagine I have this phone here now, and I have this finger here. Right now, they are not applying any force on each other. Even if they are just touching, they won't apply a force on each other. When I try to push my finger through the phone, what I am trying to do is I am trying to make my the molecules or atoms of my finger be in the space between these atoms. Alright, I'm trying to push my finger through the space between the atoms of this phone. Now, these guys have a very strong attractive force amongst each other. So they do not allow that. So please note that solids, the normal reaction is always exerted by solids, by the way. Alright, in case of solids, what happens is that all the atoms are packed together tightly. Alright. So when you try to take your hand through a solid, what happens is you are trying to push their atoms apart, and you are trying to pass this finger like this. Imagine it like this. If I put my hand in the space between these two fingers, then I can pass it through, right? This is what I'm trying to do for all the atoms present here. What I'm trying to do is I'm trying to put my finger in the middle of the atoms, and I'm trying to separate them and make my finger go through. Alright. Now I can do that with air. See, I just moved my finger through all the atoms and molecules of air which are here. Alright, so there are a lot of atoms and molecules of air present. But if I want to move my finger through them, they have no problem. They just step aside and pass my let my finger pass. I can do that for water also. If I had water in a glass and if I dip my finger, what would happen? I am making my the atoms of my finger go through the middle spaces of the molecules. I am separating the molecules of water, and I am making these molecules, the molecules of my finger, pass through them. Again, they cannot resist that. They cannot resist that because they don't have enough strong force between them. However, things become different when I try to pass this through a solid. Now I have a problem. These guys have very strong force of attraction amongst themselves. So they do not want to get separated. Yes, knife can do that, of course, with large enough. If any force is large enough, then I will be able to go through a solid also. Alright, for large enough force, you can go through a wall also. Superman can punch through a wall also. So that is not something that we are talking about. We are talking about whether this will allow it to pass easily or not. Whether this will allow it to pass easily or not. Alright. If I push something hard enough, then even solids will break. Even solids will break. Why not? See, the point is that these solids, the force of attraction between the solid molecules also has a limit, right? It will try to push back because they don't want to get separated, but they also have a limit to the attraction force that they have between them. See, if I'm putting my finger here, initially it doesn't get separated, but if I increase the force, then I will separate these fingers. Alright, I have to increase the force enough. Alright, same thing. If I can put a high enough force, or I can create a high enough pressure here to separate these two, then yes, I can do that. Alright, even for solids. But point is, solids do not allow that easily, and solids resist this. This force with which they are resisting this is called normal reaction. Alright, when I am trying to push my finger, they are pushing the finger back so that the finger does not enter this. Alright, that is what you call normal reaction. Alright. Hi Chinmay, how are you? So please remember, normal reaction is coming into play when two solids, the molecules of two solids are trying to occupy the same space at the same time. Alright. Since these guys cannot allow any other molecules to come between them, and same with the case with these. So when they are pushing, they both start pushing each other back. Imagine, let me take one more example. Let's say you have Three friends are standing holding each other's hands. Alright, let's imagine this. So three guys are standing, or maybe five guys are standing, holding each other's hands. And I am going to try to pass through them. Somebody is trying to go through the middle. What happens? If suppose they are very good friends, they are such good friends that they don't want to let go of each other's hands, then what happens? I mean, imagine it, picture it. If you are holding the hands and somebody is trying to push you, what you do is you two keep holding your hands together and you push it back. You push that thing back. That is what is happening for normal reaction. When something is trying to go through two atoms, the two atoms are holding each other together and they are pushing the object that is trying to enter back. However, if I keep on increasing the force, here, these guys can only hold things for so long. They can only hold things for as long as they have the strength to hold, right? Beyond a point, their hands will get separated. I will have to let go of the hand of the other and the thing will pass. That is what you were saying, Pawan. So if I keep on applying force on a solid, if I keep on increasing the force, there will come a point where this will break and my hand would actually go through. Alright. Like as I said in the example, like what happens, imagine if a Superman punches a wall. If you are punching a wall, I mean assuming that that wall is made with good material, good cement and all, it hopefully will not break, okay? But if Superman punches it, then of course even that wall will break no matter how strong it is. So if the force is increased more and more, then these contacts will also break and other things will pass through, okay? So normal force is that force which is not allowing that. Now the same is true for the other guy also. When this is trying to go through the molecules of this, since these guys are not getting separated, so what is happening is when I am bringing both of them together, it seems that this guy is also trying to go through this. Alright, I hope that you realize that it's not only this person pushing this guy, this person is pushing this also. So both are pushing each other. So that is what a normal reaction is. I hope you guys understood what normal reaction is. Normal reaction is acting between two solids when they are trying to go through, one is trying to go through the other. Okay, let's take it like that. Now this force is electromagnetic in nature. As I have been telling you, this example of me, bringing my finger very, very close to my hand. When I bring it close enough, the electrons of both will start repelling. So that is why this force is also similarly electromagnetic in nature. I am bringing the atoms of my finger very, very close to the atoms of my hand. Okay. So this is electromagnetic force eventually. Now, it is a push-only force. So normal reaction is a push-only force. Why? Now, these atoms have a problem only if I am trying to go through them, if I am trying to separate them. If I am moving away, these guys don't mind. So these guys will only apply a force to something which is trying to go through them. They will only push that back. Alright, if something is moving like this, then also these guys do not have a problem. Friction will come. Friction has a problem. But normal will not come. Alright, this kind of relative motion will not cause normal to come into play. If they are just touching each other, again, if a block is kept like this and another block is just kept like this, just touching each other, what do you think is the normal reaction between A and B? Tell me. Alright, so tell me what is the normal reaction between A and B? They are just touching each other. Smooth surface, two blocks are kept on a smooth surface just touching each other. What will be the force of normal reaction between them? Okay, try and answer this. What will be the force of normal reaction between these guys? Alright, come on, try to be more interactive. Zero, absolutely. Pawan is right on. Zero. Why? They still do not have a tendency to go through one another. Okay. The normal reaction will only come into play when this guy is trying to go through, when this guy is trying to separate the molecules or atoms of this. Alright. Yes, you guys are absolutely right. Till the time one guy is not trying to separate the molecules of the other, they don't have a problem. They don't apply a force. Okay. That is why this is the push only force. If it's only if somebody is trying to push their way through, they will push back, and that is why it's a push only. If somebody is moving like this, they don't have a problem. If somebody is moving away, they don't have a problem. So they don't want to pull. They don't want to pull the thing back. Alright, they only want to push somebody who's trying to separate them back. So this is a push only force and always acts along normal, common normal. Common normal means perpendicular. See, as I said again, if I apply a force like this force has two components, one this and one this. Now this component, what that is doing is, it is only making this move along the surface. So if I am moving along the surface, I am not separating the molecules here. Alright, that is why these guys do not mind that. They do not oppose this motion. They oppose this motion. So that is why this force always acts normal to the surface. Alright, I hope you can see that. Next, the force is self-adjusting. It is self-adjusting and can self-adjust instantaneously. So, obviously, if I am trying to gently push, alright, if I am pushing this gently, then my finger is not going anywhere. So I can say, if my finger was getting pushed by F, then somebody must be pushing my finger back with F. That is why it is not moving, right? From all the class 9 knowledge of Newton's laws. Alright. So if I'm trying to push my phone, alright, so if I'm trying to push it with force 1 Newton, then the normal reaction between the hand and the phone must be 1 Newton. If I increase this force to 5 Newton, now the normal reaction must have become 5 Newton. So this force can self-adjust. It can increase its value to whatever is required. Alright, if 1 Newton was required to stop this guy from entering this guy, then it will push it by 1 Newton. If 2 Newton is required to stop this guy from entering this guy, then 2 Newton would be applied. So normal reaction will take up a value whichever will ensure that this solid does not go through this solid. And it can self-adjust its values as I keep on changing my force. Now it can also adjust itself instantaneously. So if I held this steady and if I suddenly gave it a jerk, alright, so suddenly a force must have come. Suddenly a normal reaction must have come which was to suddenly stop this. Alright, so this can not only self-adjust, it can self-adjust itself instantaneously. So you need to remember this. So normal reaction can not only self-adjust, it can do so instantaneously. Alright, so these are some examples where I've shown the diagrams and where I've shown the directions of normal reaction. Yeah, don't worry, I'll take care of that later. Alright, so here, what is the common normal? So always remember guys, the direction of normal reaction is along common normal. So in this case, you have this surface and this surface. These two surfaces are there, the red and the black. The common normal to both is this. Alright, the common normal to both is this. This is the common normal to both these surfaces. Now when you're judging about the normal reaction on the block will act upwards because it's a push only. Alright, and again, according to third law, again I'm using your class 9th knowledge, okay. I hope you remember some of class 9th Newton's laws, that there are action-reaction pairs. Alright, yes. So if the ground pushed the block up by n, the block will also push the ground back by n. So this guy will also feel an n. The ground will feel an n in downward direction. Both are feeling the n's in perpendicular directions and both are feeling push forces. So block is feeling pushed up, the ground feels pushed down. So both are feeling push, both are feeling the push along the common normal. Okay, please remember this. Okay, similarly here. Here only one point is in contact and one surface. So the common normal would be this. Okay, similarly common normal here is this. Now here again, whenever there is a point and a line contact, alright, so here there is a line and line contact. When two lines are in contact, then you can easily find the common normal. when a point is in contact with a line, then also you can find the common normal. Alright, the common normal would be the normal to the line. Alright, okay, what are the normals? What are the normals to a point? What are the normals to a point? Tell me. If I have this point, what is the normal to this point? Alright, tell me. What do you think is the normal to this point? I am waiting. Tell me the direction of normal to this red point that I have made here. Tell me the direction of normal to this point. Can't say. For a point, there is no normal defined. Normal means perpendicular to a tangent. Okay. So since for a point there is no tangent, you cannot have a normal. Yes. So what you're doing is anything can be called normal, by the way. Hi Himlata. How are you? So you must realize that. Okay, for this I could have called Hi Himlata. For this can be normal, this can be normal, this can be normal. So any direction can be called normal for a point. Okay, please remember this. So that is why when I'm trying to find the common normal between a point and a straight line, then all I need to do is find the normal to the straight line only. Okay. So please remember this. So here you will see the common normals are along these lines. So these are the directions of N1 and N2. Okay, so here normal. Again, you realize from both these ends, the sphere is getting pushed. Now, similarly, here also we saw that these were the common normals. Here also, if there is a L-shaped wall and this is kept like this. So again, here is a point and here is a line that are in contact. So this is the common normal. Here again, a point and a line are in contact. So this is the common normal. So these are the directions of normal reactions, and you realize everywhere the body on which the normal reaction is acting is getting pushed. So N2 is pushing this in the direction along the common normal. N1 is again pushing this in the direction along the common normal. Alright. How about this special case? Okay, similarly here. Here, what is the common normal? It is this. These two contact surfaces will have common normal here. This small m is getting pushed in the direction of common normal. Now comes the tricky part. So imagine these are two wooden planks which are resting like this. So here I can draw a normal. This would be like this, N1. Here again I can draw, it would be like this, N2. But how about the normal here between these two? I am in class 10. My friend have IIT foundation, but I don't have. Can we crack JEE in 2 years? Absolutely. Absolutely you can. Yes, Hemlata, you can. 2 years is more than enough, but you will have to work really hard. Okay. You will have to work really hard. You will have to join a regular course. Okay, and at least study at least 6 to 7 hours a day. Okay, you do that, you will be able to crack IIT JEE in 2 years. 2 years is more than enough time. All right. Okay, no problem. I did all my IIT preparation in 1 year, by the way. So though the competition is increasing, it's going on increasing these years. In these years, but yeah, don't worry. 2 years is more than enough. I think getting a top 100 rank may be a little difficult these days. For yeah, it's a matter of where you are feeling comfortable. Okay, so I can't really say that this is the best or that is the best. It is a very individualistic thing. Okay, it is a very individualistic thing. Some people may feel comfortable somewhere, some may feel uncomfortable there. So again, it is not up to me. It is not up to me to decide. Alright, it is up to you to decide. Alright. It's not like one medicine will suit all. Right. IIT JEE is a very tough competition. tough syllabus. So everybody has their own way of learning. So I don't know. You will have to find something that suits you. All right. So as I said, on these contact points, I have two normal reactions. How about this? How about this contact? This is a point-point contact. Both the planks have single points touching each other. So how do I decide the direction of normal reaction here? So point is that I can't. I can't. So how do we do it then? What do we do? If I don't know the direction, I will assign a general direction ny and nx. We usually assign two components, then I will have to solve my equations to find these components, and then when I have found these components from all the equations, then vector sum of them will be the direction. The direction can be anything by the way. That is the point I wanted to make, that the vector sum of this could have lied anywhere. It could be like this, maybe this was negative, then it would lie here. Maybe this was also negative, then it would lie here. So it can be in any direction. The n can be in any direction. All these are possible directions of n. I can't say what fixed direction n will take. So what we do is we will just assign two components, we will solve our problems, and then we will find out. Alright, so before solving, you can't predict the direction of n in this. This is one tricky case where you cannot give the direction of n. Everywhere else, without knowing the value of n only, you told the direction. But in case of point-point contact, you cannot do that. Okay, so please remember that. All right. Next, let's talk about a small practice problem. So you've been told a ball is held stationary on a smooth inclined plane as shown. Mark the directions of normal reactions acting on the ball on the incline. So you guys should definitely try to mark the normal reaction acting on the ball and the normal reaction acting on the incline also. All the normal reactions that are acting on the incline, by the way. Mark the directions of normal reactions, all normal reactions acting on the ball and acting on the incline. So try this. I will give you 2 minutes. But you guys need to start practicing along with the lecture only. All right, I think that is where classroom teaching was more effective. Your offline teaching, because students were sitting in front of me, I would ask them to try it right away. I would maybe even call them to the board and draw it on the board, which unfortunately I am not able to do here. But whenever I tell you to try something, you do it in your copy and pen, and then when I am telling you, you try and see whether you did it right or not. So Pawan has already marked it, which is nice. So as I said, that is how you can make your classes, online classes, effective. Okay, if you start doing all this. Yes, I'm not asking you the magnitude. I'm not even asking you the magnitude. I'm only asking you to the directions. The directions. Yes, push perpendicular to the surface. So this will feel an n in this direction. Okay, how about the incline? How about the incline? The incline would feel a push in this direction and it will also feel a push from the ground because it is also in contact with the ground. So incline will feel two pushes, n and n dash. So remember this. Yes, but for incline there will be another n coming from the ground. So remember, whenever you are trying to identify n, identify the contact that a body has. Let me show you an example. So when you had to identify the ends here, what you do is you identify the contacts that this body has. So let's talk about this sphere. This sphere is in contact with this wall here, and this plank here. So I can identify 3 contacts for this sphere. Once I've identified all the contacts, now I find and apply ends in the common normal directions, which should be pushing it. Alright, so that is how you will always mark your ends. Okay. Alright, so next let's talk about the tension force. Okay. What is a tension force? So when a string or a wire is held tight, its ends pull on whatever bodies are attached to them in the direction of this string. This force is known as tension force. So essentially, it's not only the things that are attached to the ends. A string tends to pull every part of the string, by the way. Alright, so this is what is happening. So what is happening is when you're holding a string tight, when you're pulling it from both the sides, now you realize what is happening is, if I only focus on a small part, so here you can say that this guy applied a force. Okay, let's use this. Here you can say that this guy applied a force, this guy applied a force, and the net force is 0. That is why you don't see the string moving anywhere. Alright, how about this? How about if I only focus on this part? Alright, let's just talk only about this part. What is happening to this? Now, if I make only this, and I can say that this guy, okay, let's make it smaller. So this guy is definitely applying a force on this. So you have this F acting, which is this F, this F. Now, this part is also not going anywhere. So why is it not going anywhere? If one side, there is a force pulling it on one side. So now what you conclude is that this force obviously has to be balanced. So there has to be somebody else. Somebody else is pulling it in the opposite direction. There has to be some force, F dash, let's call it. So there has to be some force, F dash, which is balancing this force F. That is why this segment is not moving anywhere. Alright, now where is that force coming from? That force is coming from this part of the string. It is this part of the string that is pulling this towards this. So what is happening is, imagine just like normal reaction. This is just like normal reaction. Why did normal reaction come into play? Because you were trying to separate the molecules, right? Now what happens when you're trying to pull this? You're again trying to separate the molecules. You are trying to pull the molecules apart. But these molecules have a strong attractive force on each other. So what they do is they start pulling all the molecules back. So whenever you are trying to pull the ends of a string, there is a force which develops all around this string. Every molecule starts pulling each molecule that is trying to go away from it back to it. Alright, this is what you call tension. So tension is molecules of a string pulling the other molecules which are trying to move away back towards them. Alright, so every molecule will pull each other. And that is what tension force is. That is how it is arising. If you leave the string, if you don't stretch the string, then there is no tension force. Alright, so please remember this. The tension force only arises when you are trying to pull the molecules of the string apart. Okay. And obviously this is a pull only force, and this is always along the direction of this string. Now this force is also electromagnetic in nature. It's a pull only force, always acting along the length of the string. It is also a self-adjusting force and can self-adjust instantaneously. So if I'm trying to pull this string with, let's say, 2 newtons, so the tension would be 2 newtons. If I'm trying to pull this harder, then obviously tension would have increased. From here you can see. From here you can see that if this is not moving, F dash must be equal to F. Alright, so you realize if I change my F, I will change my F dash. That F dash is called the tension. Now we usually represent that as T. This, we say this is being pulled by T. Now again, according to third law, if you talk about the rest of the portion, if this applied F dash, then this will apply F dash on it back. So you see, every part of the string is pulling the other part. This part, okay, this part of the string was pulling this part towards itself. Similarly, the part of string here is pulling this string towards it. So this is what happens when you make a string tight. Every small part of the string starts pulling the other part towards it. This is what tension force is. Now you usually represent this by T. Alright, you use the symbol T to represent. It is a self-adjusting force, and again this can also self-adjust instantaneously. Imagine if this end of, there is an end of a string which is fixed, and if I suddenly pull this end, so suddenly a tension must have come, so this force can self-adjust itself instantaneously. Now comes the important point. If the string is massless, then the tension T has the same magnitude at all the points. What do I mean by that? You realize I told you that this string, if it is in equilibrium, then f dash equals f. Now I could have taken another part here, and here I could have said, if I make the FBD of this, or if I draw the forces on this, so what do I see? That this is getting pushed here with f dash. Here also it must be f dash. So what you realize is that the force of tension is same everywhere, as long as either the string is stationary, so the acceleration is zero. So F equals ma would tell me net force is zero, or string is massless. If string is massless, then what happens? If you apply F equals ma, m is always zero. So F always has to be zero. That is why the tension force always has to be uniform in case of a massless string. Now all your ideal strings are usually supposed to be massless. So please remember, if somebody has told you your string is ideal, then you will use this fact that in case of massless strings, the tension has the same magnitude at any point of the string. Alright, so I hope everybody followed this. So let's talk about this. So mass is being held with the help of a lever and a string as shown. All you have to do is mark the direction of tension force acting in the string at various points of contact. So what are all the points that the string is touching? String is touching here, string is touching here, string is touching here. So what will be the tension forces that the string will be applying at these contact points? So that is what you have to mark. Alright. So let's just do this. This is easy. On this point, you will say that the string is pulling with tension T in this direction. This point, it is pulling in this direction. Again, you realize the tension force always has to be along the string and has to be a pull only. So whatever string is touching, it will pull it with T. So here it is pulling it with T. Here it is pulling this with T. Here this will pull this with T, and this will pull this with T. So everything that string is touching, it starts pulling that thing with tension. Alright. So I hope you guys know how to mark the directions of tension, always along the length and always in the direction of pull. Okay. Alright. So these are some examples of tension forces. So here you will see the tension on this is in this direction, tension of this is in this direction. Similarly, if I have these two, if you talk about this, the tension here is acting on this direction, the tension of this is acting in this direction. Here, if a block is here like this, then this on this tension acts in this direction. On the pulley, the tensions are acting here, and on this end, the tension would have acted here. Alright. So if you practice it a little, you should be fine with marking your tensions. But please note, it is very, very important that you start marking your forces with the correct directions. Alright. I am September 2 shift. You told you will complete thermodynamics. I am starting thermodynamics today, Jay. Today I am starting thermodynamics at 9:15. Okay. So you still have 6 days to go. Don't worry. In 6 days I will try to finish thermo. Okay, Jay. Don't worry. I will extend the classes if I have to. Don't worry. I will try to definitely finish thermodynamics before your JEE, or by the 31st of this month only. Okay. So we still have like five days, and 6 including today's day, by the way. So 6 days I will take up maybe 2 hour sessions each day, and we should be able to revise it. Don't worry. Okay. All right. So these are the forces. Then aside from this, there is spring force, but today we are running out of time, so we will talk about this force tomorrow. And tomorrow we'll continue our discussion from, day after tomorrow, we'll continue our discussion from here. Please pay close attention to this chapter and follow everything that is being taught. If you start following everything from right here, then trust me, your entire physics would be sorted. So that is why I'm taking these things extra slow. Okay. Oh, okay. Okay, Jayakash, I will try to teach from basics. Okay. Alright, though that 2020 series is mainly supposed to be revision, but okay, I will try to discuss basics also. So as I'm saying, for 2022 aspirants, I'm taking things very slow. I'm taking my time in explaining the directions of normal reaction and tension. I'm taking my time in explaining how normal reaction acts, how tension acts, why they act the way they do, so that you guys can follow every small little detail. And trust me, if you do that, your physics would be sorted. All right. So, in keeping this, in this spirit of keeping things slow and detailed, I'm going to stop the lecture here. We will discuss these parts when I see you next, which is day after tomorrow. So that is it from me. You guys watch the video. Make sure you are understanding everything that has been discussed today. If there's any confusion about any part, then you can discuss that in the next class. All right. Please make sure you do that. Now, before I leave you, let me remind you how to get your Unacademy subscriptions. It's very, very easy. Once you have downloaded the app, go to the plus section, select your goal as IIT JEE and click on get subscription. Alright, I am good, Shivendra. Thank you for asking. Alright. Now, when you're getting your subscription fees, please note that your fees are already very, very affordable. However, you can make them even more affordable by using this code. So when you're getting your subscriptions, use this code RDLive to unlock all the great features of the Plus, Unacademy Plus, and also get an additional discounts, which makes this fees even more attractive. Alright, if you like today's video, if you think you learned some new things, and if you think I helped you understand your basics better, then press the like button, share it with your friends, and don't forget to press the bell icon. Alright, press the bell icon to get all the notifications of all the sessions that I'm conducting here. The PDF of all the slides that were used in today's lecture would be available for download within 2 days. Okay, so give me 2 days time to upload all this. And don't forget to join us on the Telegram app using the link shown above to get all the notifications of all the things that are happening on the JEE English channel. Next, before I leave you, let me remind you one more time, my code is RDLive. Use this code to get your Unacademy subscriptions and get an additional 10% off. So I'll see you next, I think day after tomorrow on Friday at 4. Okay. So till then, you guys take care, read your notes and keep practicing. Bye-bye.